yeah, it's interesting to know about it.
It happened on Tuesday.
I wasn't like thrilled about the story. But anyway, welcome people watching this video. Hopefully you're having a good time in Ashland or not, whatever you want. We're going to go back a little bit and we're going to graph the reciprocal functions once again, move on to damped graphs, and then I'm going to give the class time to work on their proof pass. And because I'm a kind of a pushover, the class before this on Thursday got me to agree to a review day because this stuff is, quote, hard, unquote. So you will have a review day, but make sure you're actually doing your proof pass. And like I said to last class, the proof pass, I'm going to make it so everybody's going to take the test, whether you complete a proof pass or not. So you will be taking that test, but I'm going to warn you, if you don't do the proof pass, you'll probably fail. Because the proof pass is just basically a arm's length away from what's on the test. So do the proof pass. Not required. It will be graded, but not required to take the test. Got it? They all nodded their heads. Okay. Shut up. Shut up. They did. Well, most of them nodded. Kim kind of shrugged, but the rest of us nodded. All right. So we were talking about cosecant and secant. Did I not clear all these out? I thought I cleared all these out. And kind of rushed through the lesson yesterday, so we'll go back and get a double refresher. We're going to go ahead and leave that one as is down there. And we talked about the idea behind this. And cosecant, if you remember, is 1 over sine of x, and secant is 1 over cosine of x. So they're going to be really close to cosine and sine. And I think we graphed it, but we didn't fill in all of these things. So let's first talk about the period. The period for cosecant of x, that is 2 pi, as well as secant of x. The domain is all real numbers, but for this one, we have a situation where it cannot be 0, because 1 over 0 is undefined. And so we have to think, when does sine equal 0? Well, sine equals 0 at every pi value. So we're going to say n pi. Hello. Not here. I think they might be in Ashland. Maybe Maria's in Ashland? Yeah. Never mind. No, not here. Not here. Sorry. Have a good day. What? So, to fill you in, a person came in and asked and gave me a little slip, and then that was for Maria. So, Maria, you have a slip waiting at the front office. I didn't read anything. I thought I saw something about graduation, but I'm not going to eavesdrop. So, good.
I'm nervous. I was just like, I'm not graduating.
No.
Freaking out.
No, it was like about cap and gown stuff.
You don't get one if you're not graduating.
I'm going to have to stop this. I might have to bleep all this out. Did you guys ever watch that video?
No.
Oh. I bleeped a bunch of things out. Anyway, range. What is the range? Well, the range for these ones are very interesting. It's actually like the general range of this particular one is technically that x is greater, or excuse me, y is greater than the amplitudes. That's what it generally is. But for this one, it's actually y is greater than or equal to 1, or y is less than or equal to -1. That's our range. Yeah, come on forward. There's only 6 of you.
Well, I just couldn't see and I was like, I might as well just do that.
That's your new assigned seat. Linda gets to move back.
No, Linda can keep her spot.
Okay, vertical asymptotes. Vertical asymptotes are whenever we have issues with the domain. And I really should put does not equal x. Because the vertical asymptotes are x equals those values, n pi. Symmetry for sine is going to be odd. There we go. Why is it odd? Well, what the frick? What the frick was that? That was a flea. Oh my god! That was a flea. What's a flea doing on me?
You have fleas.
Oh, God. Don't have
But I don't have gall darn fleas. Gotta watch my languages.
Oh, my goodness. Darn.
That was freaky. Little tickling on my arm, and I see a little black guy and jumps right on my shirt. Pretty sure I smacked him real hard, but yes.
The other day, you said the vertical asymptote was sine x equals 0. Is that the same thing?
Yeah. So this is that's actually true. When
You said that.
but this, if you notice, if I plug in n for 1 or 2 or 3 or 0, that's when we're having the vertical asymptote. So, look, see up here? Whenever sine x equals 0, we have 1 over 0. That's what we're saying. And that happens whenever sine x equals 0. So I could put when sine x equals 0. Because sine x equals 0 at 0, pi, 2 pi, 3 pi, 4 pi, 5 pi, 6 pi, 7 pi, n pi. Okay? At all the n pi's, that's when sine equals 0. So that's why I said that. Now for cosine, the domain is pretty similar, but cosine, when is cosine 0? That's at intervals of pi over 2. So x cannot equal pi over 2, and then we're saying, and every pi that happens afterwards, plus n pi. And once again, n is an element of integers.
Wait, what does that mean?
It is a whole integer. So n is like 1, 2, 3, 4, 5. N is not 1 half, 2 halves, 3 halves, 4 halves, 5 halves. 1.362, yeah. 3.1419284. Not pi. Made you look.
No, it's...
I know. Anyway, the range for this one is also the same thing. Y is greater than or equal to 1, or y is less than or equal to negative 1. Okay. At this rate, we're probably not going to finish the lesson in time. So I think I need to focus a little. Vertical asymptotes, those are at the spots where the domain is bad. Okay?
Okay.
So we get pi over 2 plus n pi equals x. That's when we have vertical asymptotes at every pi over 2. So pi over 2, 3 pi over 2, 5 pi over 2, 7 pi over 2, 9 pi over 2, 11 pi over 2. All of those are going to have vertical asymptotes. Okay? And then we have symmetry. Symmetry for this one, if you remember, cosine goes like this, and the symmetry is over the y-axis. If it's over the y-axis, that means it's an even function. Because this one goes in this direction, so it is also even. Okay? There. This one's odd if you look, because sine starts right here. And so we have it going up here. And then we have symmetry over actually the origin. So there's symmetry over the origin. Alright? Here's your little step-by-step. We're going to first identify the reciprocal and graph that with a dashed line or a different color line or whatever you need to do. And then step 2 is at the x-intercepts of the reciprocal, we're going to put vertical asymptotes. Whenever that graph crosses the x-axis, put a vertical asymptote. Each max and min of the reciprocal are vertexes of the parabola in the opposite direction. And then you draw it. And that's all you have to do. Okay? So let's do that. Did we do this one?
Yeah.
We did all this already. Okay, good. So that means I can speed through this.
Not the graph of secant of x.
Okay. Let me just clarify this stuff. 2 pi. Increments are pi over 2. And so we end up going 0, pi over 2, pi, 3 pi over 2, and 2 pi. Okay. And then our starting point was 0 because it's our regular function. And so we get 0, 1, 0, negative 1, 0. And so whenever sine is 0, we have undefined for cosecant. But we also have those values of 1 and negative 1. Those are the same. Okay? And I'm pretty sure...
How would we multiply that?
What?
How would we multiply that?
When there's something out in front.
Okay.
Yep. So I'll just do one period here, get an idea. I won't even label it. There's that, 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 and that. So there's sine if, we have pi over 2's, going by pi over 2's. And now we are going to draw the asymptotes here at the zeros. And right here. And then the vertex of the parabolas are at our peaks and our mins. And so we have a parabola that goes up and down and down. And there it is. You draw something like that, I'll get the point. Okay? That was fast. Let's do it again for secant. Okay. So, secant of x is the exact reciprocal of cosine of x. So we have the same period, 2 pi. Our increments, same stuff. That is going to be pi over 2. And our starting point is still 0. So we can go 0, pi over 2, pi, 3 pi over 2, and 2 pi. And we can fill in our regular cosine values. Cosine of 0 is 1. Cosine of pi over 2 is 0. Cosine of pi is negative 1. Cosine of 3 pi over 2 is 0. And cosine of 2 pi is 1. And then, like I said before, secant has the same values, but whenever we have 0, it's undefined. So we have 1, undefined, negative 1, undefined, 1. And now we can graph. We're going to graph cosine first. We're going to go by 2's here again. But this one, let's go by 1's. Let's go by pi over 2's every tick here. Pi, 3 pi over 2, just so you can get an idea of what happens afterwards. Okay? And we'll go the opposite direction as well. Boop, 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 boop. Okay. So let's graph these points. Let's graph them with a different color here. Let's graph them with orange. Is that hard to see? No, that's not that hard to see. Here's our first point right up here. 1, 0, negative 1, 0, 1. Repeat. 0, negative 1, 0, 1, 0, negative 1. And the other way. Dum, 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 dum. There we go. Good. Okay, and we just need to draw a little line here. Oh, wow. So far, so good. Wow. Wow. That looks great. Whoa. 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 Yay. Whoa. There we go. That last one wasn't very good. That one was a lot better. Alright, we good? And now we draw our vertical asymptotes whenever we have a 0. There's a 0 here. There's another 0 here. We got a lot of them. Notice these are at every pi over 2. That's what we said on that one slide where we were naming all of the vertical asymptotes and all the times when cosine, or sorry, excuse me, secant is undefined. Got our vertical asymptotes. Alright, and then once we get those vertical asymptotes, we can draw the parabolas with the vertex at the max and the min. Okay? Yay. They're going to look really cool here. Okay, and then time to do parabolas. So I'm going to pick a completely different color, purple, and we're going to do parabolas. There's one right in the middle. There's one right here at that little max, at that max, and then all of these little mins here. There they are. Now if you get a little halfy over here, you just put half of it. Sometimes you'll have to graph a half. Like that. There's a lot of what? Yep. One off of every peak or every minimum. There it is. So basically it's all the purple that we're looking for. Okay? Good. Good, Traben? Really, I figured out your name. I think I got it down now. Okay, so are we good? Is people still graphing? Just too small of you. You have to speak up. I can go on. Alex? Cody?
You good?
Alrighty. Let's make like a tree and let's go to the next slide. That's not what I meant.
Come on, say the rest of this, Guido.
And leaf? That's not a very good, joke. Alright, so we are going to do this one. Now, this one is pretty standard, okay? We are going to graph, mainly I want to be able to graph this, but to graph this second function, we need to graph our first function. The cool thing is, after you graph y equals 2 sine of x plus pi over 4, all you got to do is put vertical asymptotes when it hits 0, and I forgot what I was going to say. Put vertical asymptotes at the 0, and then we draw our parabolas off of the maxes and mins. That's all you got to do. And then you have cosecant. But we have to figure out where do we start, what's our period, stuff like that. What is our period for this one? What do you think, Kim? 2 pi. Nice, Kim. Our increments then would be 2 pi divided by 4. What's that, Cody?
Sorry.
2 pi divided by 4?
2 pi divided by 4? 2?
Pi over 2. That's our increments. Hey, that's nice. Now we just got to figure out where do we start. Well, we do have a shift. Now, our value is going to be back pi over 4, but it's always nice to do it the way I've taught you, which is you set 0, our original starting point, equal to x plus pi over 4, and see where we end up at. And we end up at starting point of negative pi over 4. So we're going to do negative pi over 4. And then we're going to go by increments of 2 pi. Pi over 2. Increments of pi over 2 until we get to a full 2 pi. Not until we get to the endpoint of 2 pi, but until we do 2 pi amount, which is basically 5 spots. Okay? So add pi over 2. That's the same thing as adding 2 pi over 4. So I want to add 2 pi over 4 here, and I end up getting pi over 4. I'm going to add another 2 pi over 4. I get 3 pi over 4. I'm going to add another 2 pi over 4, 5 pi over 4. And I'm going to add another 2 pi over 4, and I'm going to get 7 pi over 4. See how that works? Now, we're going to streamline this process. I want you to remember, I'm going to write this down, but I want you to try to do this without writing these down. 0, 1, 0, negative 1, 0. Don't write those down. If you need to, you can. But the streamline process is you just take those values and multiply them by 2. So 0, 2, 0, negative 2, 0. Okay? If you want to write those original values down, it's good to repeat them all the time. And guess what? 2 cosecant x? Pretty simple. 2 cosecant x is undefined 2, 0, nope, undefined, sorry, negative 2, and undefined. See how that works, Cody? Cool. Get off your phone. Now we can graph it. Let's just graph full period here. We're gonna graph we're gonna go by 2's. Okay? And now this one's a little funky because in fact I'm going to go ahead and just do this as negative pi over 4. 0. Oh, actually, that's right. I forgot about this one. This one we have to go by 1's. Negative pi over 4. 0. Pi over 4. And then that would be 2 pi over 2, and this is 3 pi over 4. This is something. This is 5 pi over 4, and this is 7 pi over 4. Just has to make sense. And let's go ahead and graph it. Let's go. There's 1 and 2, negative 1, negative 2, and we're going to graph this in red. Nope, I botched that one. I gotta actually look at the values. There we go. There we go. Okay. I forgot like a tick mark right there. Right here. Okay. So now we have our sine wave. We're going to draw our vertical asymptotes at the zeros. And then we're going to put parabolas off the peaks. And down here. Okay? Did you guys get that? Thank you, Taylor. Yeah, Caitlin got it. Okay. Makes sense. Even though it doesn't matter that there's a bunch of crap happening over here, it doesn't matter. All you have to do is deal with that sine. And once you deal with the sine, there's parabolas coming off of it. Okay? And they're going to be more... Now, it is true that they're going to be steeper. So, like, this technically would be a little bit steeper here because what's below it is a little bit steeper. Do you see that? It's going to have a similar shape to that first part, really. But, I mean, I'm not going to be a stickler about that. I want you to know how to graph in general. Okay? We good? I think we're done with those. And we're off to damped graphs. The ones that are left in the water, circa Traben said that first. Okay. Yeah. Side effects include bleeding from the eyes, nausea, diarrhea, gout. All right, so that's probably only funny to me. It's all right.
Come on up here, Mom. Yes, me.
Oh, brother. Okie dokie. Let's continue. Damped. That graph. Here it is. This is when two functions collide. We're going to take a regular old single function, and we're going to hook it up with another single function, and they're going to become a couple. And then what they're going to produce? Never mind. Little baby functions. It's a wave. It's a baby wave. Okay? I said that to my concepts of algebra kids yesterday, and I said, here's the parent function, because we talked about parent function. I'm like, and this is the baby function. I go, and you guys should know about that because you've been studying the reproductive system. And they were all like, what? And then this girl goes, no, I have a brochure. It was the like ovaries and stuff. That's funny though.
I thought you did the same part.
On topic. This is when two functions collide. Here we go. The product of two functions can be graphed using properties of individual functions. Okay? Now, important thing here is that the function in front are boundaries for the graph that is second. Okay? And what you do, no matter what that function is in front, you are going to graph the absolute value of it, of the positive version, right here, and the negative version. So even if you had something like, for example, you had x squared, and then you did sine of x, you would graph absolute value. You're going to graph that as a boundary, and then you're going to graph this as a boundary, negative absolute value of x squared. Okay? Those are your boundaries. And what that means is that your graph is going to exist in between those two. So here's your two boundaries here that we just created, and your graph is going to squeeze itself in here. And what happens is that when it squeezes itself in between those two boundaries, we have certain properties, and we can just plug stuff in, and you're going to see that it actually makes a wave that touches those boundaries but doesn't go past them, like that. And this one, for this one, it actually starts down and goes up. Like that. Okay? And that's what our wave looks like. These boundaries actually aren't there, and so we get this graph that looks something like that. It's kind of funky looking, but the boundaries we're going to graph as dashed lines. Now, I'm not going to do very many difficult ones for you. I already made that mistake last class where I did a really hard one, and it was really, really difficult to graph. Okay? But we're going to graph this one. X sine of x. Okay? So, ones that are going to be linear functions, the ones that I'm going to probably look for are linear functions that go through the origin. Okay? Those are the ones that I'm looking for. I'll show you a few other ones, but mainly that go through the origin. Okay? So what we're going to do is we're going to graph our boundaries. Now, remember, we're going to pick values that are nice for sine of x. We are going to do that. The problem with that is when I pick values such as 0, pi over 2, pi, 3 pi over 2, and 2 pi, when I pick those, my y-axis here is going to change as well. Okay? So this one is going to go by pi over 2's. But my y-axis is also going to go by pi over 2's. The reason I'm doing that is so I can simply graph x. I'm going to graph the absolute value of x, and I'm going to graph the negative absolute value of x. Okay? And when I do that, that means I can have that V shape still if I go by the same increments. If I change these increments to 1, then my graph looks funny. But if I have the same increments over here, it's going to make things a lot nicer. So go ahead and graph, maybe with a dashed line or a bunch of points or whatever. A dashed line, the absolute value of x, which is a V, and the negative absolute value of x. So there's that. And then the negative absolute value of x is like this. You're going to have one of these questions on the assessment, and it will be pretty basic, like this one. Nope, not going to use this one. I might use cosine. I might do 2x, so that it's a little bit steeper, that kind of thing, okay? And then I am going to think about my values of sine, okay? So we're going to go through this, and what I'm going to do also here, this is going to be a little bit troubling to you because I'm going to add a column here for x, and I'm going to graph the negative version. So 0, negative pi over 2, we have negative pi, we have negative 3 pi over 2, and we have negative 2 pi. Do you understand that that would be the other direction? You see that? Okay? And so we're gonna label these, and I'm going to label these, I think I'm going to go by 2's. No, I have to go, yeah, no, I can go by 2's. 2, 3, 4, and I'm going to do the last one as well. Okay, so that's pi over 2. That is pi. That's 3 pi over 2. That's 2 pi. And this is 5 pi over 2 out here. And then we're also going to do the negative stuff as well. Now these graphs are much more unpredictable than sine and cosine graphs. Okay? Like sine and cosine graphs, you know, you do your shifts and stuff like that, and you can basically graph it. These ones are a little bit more unpredictable. Okay? So what we're going to do is we're going to think about, let's fill in this table right here, and we're going to cut it in half, and we're going to do the 0, pi over 2, pi, 3 pi over 2, and 2 pi, and then we're going to go backwards in this direction here. Okay? So let's think about this. When I plug in 0 for x, sine of 0 is 0, right? But if I plug it in for x, I have to now plug it in to 2 locations. So this is 0 times 0. Turns out, nice, this is 0. Okay? And when x is 0, we get that. Okay? Make sense? Now, if I plug in pi over 2, I'm going to plug in pi over 2 here, and I'm going to plug in pi over 2 here. What is sine of pi over 2? Unit circle. What's the y value of pi over 2? 1. It's 1. Okay? Now if sine of pi over 2 is 0, or sorry, if sine of pi over 2 is 1, I still have to multiply it by that x, which is pi over 2. So rather than it being 1, and I mean, maybe you guys need to write these down, 0, 1, 0, negative 1, 0. Those are our regular values of sine. Okay? 1 multiplied by pi over 2, our answer is actually pi over 2. Because it multiplies by that x. I pick an x that's good for sine, and I get a value out of it. Does that make sense? Okay. Does that make sense over there? What I'm doing? Same thing with pi. If I plug in pi, I get 0. But it is 0 times pi. 0 times pi is 0. The next one's a little bit more funky. We have 3 pi over 2. What's sine of 3 pi over 2? I need people to answer. There's not enough of you.
I don't have a unit, sir.
You don't have a unit that you don't have your purple sheet?
No, because you never printed me out.
I never printed you off on it.
Yeah.
Negative 1. Okay, we'll get it to you. I'll get you one in a minute. Negative 1. Okay, so that's negative 1. But this is negative 1 times 3 pi over 2. So this is actually negative 3 pi over 2.
It's negative 1.
Negative 1. So here's what I'm doing. I'm taking x and I'm plugging it in. So I get 3 pi over 2 times sine of 3 pi over 2. You see how I'm just plugging in that for x? Sine of 3 pi over 2 is negative 1. So we have 3 pi over 2 times negative 1. We get negative 3 pi over 2. I'm doing this column right here. This column's this column. I kind of neglected the second column. We'll get back to that in a minute. Okay? And then 2 pi is 0. Okay? And then it repeats itself. Let's do the other column. Okay? We'll call this the box column. We've already have 0. Now if I plug in negative pi over 2, negative pi over 2 on the unit circle is down, right? And it's at the same location as 3 pi over 2, so I end up getting negative 1. And negative 1 times negative pi over 2 is positive pi over 2. Okay? I can do that for you over here. Negative pi over 2, sine of negative pi over 2. I get negative pi over 2, sine of 3 pi over 2, because I added a period to it, so I'm going to add 2 pi to this to get this. Okay? And now we can see, oh, that's equal to negative pi over 2 times negative 1, which is pi over 2. Does that make sense now? Okay, so look at this. What's funny is that these values are all the same. They're going to follow that same pattern. It's just the other direction. So this particular one follows the same pattern, just the other direction. Okay, it's not always true that way. Sometimes it reflects, sometimes it doesn't. Like with x squared, if x squared was in the front, it doesn't do that pattern. It goes the opposite way. So let's graph these points. Now the cool thing is that we decided to go by pi over 2's. So at every little tick here, we're going to go by pi over 2. And that makes it nice to graph. It makes it really nice to graph, in fact. Okay, there's pi, 3 pi over 2, 2 pi, and 5 pi over 2. Okay? It's really nice to graph because our first point, we'll graph this in blue, is 0, 0. It's right there. Okay? So we're graphing this and this, and then we're going to graph this and this. So we have pi over 2, pi over 2. So we go over pi over 2, up pi over 2. There's a point. We have pi and 0. We have 3 pi over 2 and negative 3 pi over 2. That's down here at that particular point. It touches these boundaries. And then we have 0 again. And then 5 pi over 2 would be positive 5 pi over 2 as well. It would be way up here. Okay? And while we're at it, let's graph the other side. Okay? So when we have 0, we have 0. When we have pi over 2, or when we have negative pi over 2, so I'm graphing these now. Okay? Negative pi over 2, we have positive pi over 2. We have negative pi, we have 0. We have negative 3 pi over 2, we have negative 3 pi over 2. We have 2 pi, we have 0. And then back up to the top here at 5 pi over 2, negative 5 pi over 2, 5 pi over 2. What does that graph look like? Starts out with a little loop. Comes up, hits. Comes down, hits. Comes down, hits. Comes up, hits. Goes way up and hits. Same direction, same look. And that's what it looks like. So it goes out and it gets bigger. It gets real big. And if you notice, it just touches the boundaries. It's in between those boundaries. It won't go outside those boundaries. It will stay in between those boundaries. Okay? Good?
Could we have graphed it without graphing
Could you have graphed it without graphing
the boundaries?
the boundaries? I suppose, yeah. The boundaries are nice because they get a nice visual of it, but you could graph it without the boundaries. Okay? We also get ones like this. These are a little bit harder. This one is actually 1 over x squared plus 1 sine of x. And so what you have to do is you have to graph that and, well, the absolute value of that, and then the absolute value of the negative version of that. Okay, so you're going to graph both of those as your boundaries. And if I'm correct, these boundaries are, let me make sure I do this right. That's right, they're weird. So one of the boundaries is like this. Whoa! It goes like this. And the absolute value negative, it actually goes like this. I made a mistake last class. And guess what? When we do sine of x inside of it, it literally just kind of goes like this. And it stays within those boundaries. Okay? It's pretty hard to see on your graph. Oops. But that's what it does. And you can figure out those x values. They're going to be funky. They're going to be decimals. Okay? You might get to a point where you find all these nice ones, but you start having to square pi over 2 and 2 pi. Squaring those is not fun because you get decimals. And those decimals end up being within those boundaries. Okay? There was another one here that we did in class, last class, and basically what it did is you graph these lines that are actually out here, the absolute value lines, and your graph bounces at those spots. Not as exaggerated as this, but it does that. Okay? Alright. Kind of weird. And look at what we did here. We found decimals. Because you have to find decimals when you take a half. You have to subtract 2. You can't graph 3 pi over 8 minus 2. Oh, excuse me. You can't graph 3 pi over 8 minus 2. You can't do it. Alright. I could do one more maybe, if you'd like. Or you can get to your proof pass. Your proof pass one and your test one are going to look like this. They're going to be similar to this, okay? And that was the homework that was assigned last class. But you can turn it in today, or you can turn it in Wednesday? Oh, jeez, Wednesday. You're testing Friday? Are you flipping joking me?
At least like your period that you're giving up to let us study turned out to be short.
For you guys. All right, see you later, folks.